Welcome back, everyone. Over the last few sessions, we've introduced the SI base units, things like meter for length and seconds for time, Kelvin for temperature, kilogram for mass. In our last meeting, we discussed modifying those base units with Greek prefixes. So going from grams to kilograms or meters to nanometers and that sort of thing. In this video, we're going to introduce the idea of a derived unit. And really, a derived unit is just some combination of those base units or of those units that include prefixes as well. Pictured here is Eliud Kipchoge, the greatest distance runner of all time. Last year, he ran a marathon in under 2 hours. If we wanted to, we could calculate his average speed, and we're going to do a rough calculation right now. In that race, a marathon is approximately 26.2 miles. He was just a few seconds under the 2 hour mark, but if we just wrote 2 hours below that miles, and we divided 26.2 divided by 2 hours, we would get, go back, we would get roughly 13.1 miles per hour. Now, that combination of miles per hour or miles over hour is a derived unit. It's the derived unit for speed, distance over time. It's just not an SI unit. So let's use a similar combination, but this time using our SI units instead. Here's Usain Bolt. He has the world record for the 100-meter dash. I think it's in 9.59 seconds. But this is a breakdown of one of his races in which he ran 9.69 seconds for 100 meters. To the right, I have a table that includes his time and distance for every 10 meters along that path until we get to 9.69 seconds at 100 meters. I've also graphed that data, and you can see for the most part, it's pretty linear. It's not perfect because he's slow at the start and speeds up and eventually starts to slow down again, but it's close to linear. If I wanted to, I could calculate his speed at any particular moment of the race. So, for instance, let's see how fast he was moving at 50 meters into the race. Well, speed is distance over time. So if I take 50 meters and I divide it by the total time at 50 meters, 5.5 seconds, that's going to give me an estimate of his speed at that moment in time in the race. You would notice if you went to other points during the race, his speed is a little bit different. So at 50 meters in 5.5 seconds, he's running 9.09 meters per second. That's his speed at 50 meters. Now, overall, we could calculate an average speed for Usain Bolt. Remember, he's slower at the beginning, and so that will bring down his average just a little bit. But he speeds up really through the first 70 or 80 meters. So how could we calculate not a particular moment in time or at a particular distance, but for the whole race, what was his average speed? Was it faster or slower than the 9.09 meters per second? That's one of the reasons that I actually put the graph up on the board, because if you take a look, I have an equation and it's tough to read, so I'm going to rewrite it right now. Um, the best fit line for his race says that y is equal to 10.901 x minus 8.0212. I want to focus in on that 10.901. Think about what slope is. That's our slope for this particular equation. But slope is just rise over run, right? So in this case, you could think of it as y over x. My y-axis here is distance in meters. My x-axis is time in seconds. And so when I find the slope for that entire race, what I'm really finding is his average speed during that race. In other words, this 10.901 represents y divided by x, or meters over seconds. That's his average speed for the race, which is quite a bit faster than he was at 50 meters into the race. In a chemistry classroom, we use all sorts of derived units, and we're going to focus on just one today. We're going to talk about volume. I want you to remember that the base unit for length is the meter. If we wanted to, we could calculate something like area by measuring the two sides of a flat surface. So let's say I have a square that looks like this. And let's say that that square is 2 meters on this side and 2 meters on this side. The area of that square would be equal to 2 meters times 2 meters. That's actually equal to 4 meters squared. In other words, I have to multiply the unit as well as the numerical value that's associated with the length. We use area occasionally in chemistry, but it's more common for us to use volume. And volume is a unit that involves 3 dimensions. You can think of it as length and width and depth or height. Okay. So instead of looking at 2 sides of a square, we would have to look at 3 sides of a cube. It might look something like this picture on the next slide, where I have, let's say, 1 centimeter deep, 1 centimeter long, and 1 centimeter high. And if I calculate that area or that volume, it is 1 times 1 times 1, or 1 centimeter cubed. Okay. In our particular class, technically, the SI derived unit for volume is a meter cubed. But that's a really, really large volume. It takes up a lot of space. And so it's more common for us to use things like the centimeter cubed or the decimeter cubed. These two actually have very common different names that you're familiar with. The centimeter cubed is the same thing as a milliliter, and the decimeter cubed is the same thing as a liter. That's really important to remember. So I'm going to emphasize that again. 1 centimeter cubed is equal to 1 milliliter, and 1 decimeter cubed is equal to 1 liter. We measure volume all the time, specifically, frequently, I should say, of liquids. And the instruments that we use to do that, when we really want to accurately know the volume of a liquid, we might use something like a graduated cylinder pictured above here. Or if we wanted to transfer liquids from one place to another, we might use a beaker pictured here. If we wanted to be able to stir a liquid, we might use something like an Erlenmeyer flask, which is also known as a conical flask. It's used for stirring because it won't easily spill out. So we do measure volume all of the time. think it's really important to note that there is a surprising relationship between centimeters cubed and decimeters cubed. On my Greek prefix chart, centimeters and decimeters are only 10 apart. In other words, there are 10 centimeters in every 1 decimeter. And so you would expect maybe there's 10 centimeters cubed in 1 decimeter cubed. But it doesn't really work that way. If I cube something, I have to cube not only the numerical value, but the unit as well. So there are 10 cubed centimeters cubed in 1 decimeter cubed. Simplifying that a little bit, that comes out to 1,000 centimeters cubed for every 1 decimeter cubed. That's just another way of saying that there are 1,000 milliliters in 1 liter. There are, of course, many other derived units that we're going to study in chemistry. Our next one is going to be density, but we'll save that for another video. Take care.